Okay, so there are a couple of other parameters besides differential mode gain and common mode gain. So, and one of them is what we call as a input common mode range. Now, in earlier analysis of differential amplifiers, you may not have seen this particular parameter, but it's fairly important, input common mode range. And let's look at the motivation for it. Here is a differential pair, and what we have done is we have connected a bridge to the differential pair. You can think of this particular bridge as, let's say, this one is a sensor, could be a pressure sensor, right? And so what happens is normally the bridge is balanced. The value of this particular voltage, this resistance is same as this resistance. The bridge is balanced. And when you apply a pressure, the resistance changes and it results in development of some voltage here, which is then supposed to be amplified. So when so what happens is when you excite this particular bridge here, let's say using 5 volt, what would happen is normally the voltage at this point, let's say if all of them are equal resistors, the voltage at this point will be 2.5. The voltage at this point will also be 2.5, basically a voltage divider. Now when you apply a pressure, this resistance changes, and what you get is 2.5 plus some signal voltage here. Signal meaning a voltage which is proportional to the pressure applied here, right? So, but what you note here is that you get on the other arm, you get 2.5. On this arm, you get 2.5 plus the signal. Now, what the reason why we are using a differential pair is that we want to reject the common mode, 2.5. We want to reject the common mode and amplify only the signal here. So what you see here is that from when you're using differential pair, the signals that will come to you will be embedded in a common mode, and unwanted, usually a common mode part as well. So 2.5 volts is an unwanted part here. So now what we are interested in is the signal voltage. We want to amplify this signal here and amplify it so that it appears here. Now what happens is, as you change the common mode part, what happens is if you make the common mode voltage too large, you will find the differential pair will not work properly. In the sense, for example, we'll see if it's 2.5, it's okay. But suppose I make it 3 or 3.5 or 4, you may find that the differential amplifier doesn't work properly. Doesn't work properly mean that the differential gain, for example, may drop. So differential gain depends on the common mode signal that you apply. As long as the common mode signal has a value which is reasonable, you will find differential mode gain is insensitive to it. But if you make the common mode voltage too large, input common mode voltage too large, you may find differential mode gain drops. It's no longer high. It drops significantly. Similarly, you may find that the common mode gain changes significantly, may become large. All right. So the differential amplifier, the idea is that the differential amplifier will operate properly only if the common mode input that you see here is less than a certain value. Okay. Then it will operate properly. If the common mode input is larger than a certain value, you'll find differential amplifier fails to work properly. And we have to understand what are those limits. What is that input common mode range? What is the input common range, which means what is the maximum positive value of VIC that I can apply and things will work properly. And similarly, what is the minimum, which means negative common mode input that I can apply and still the differential pair will work properly. So here I'm showing you an example of a bridge connected to a differential amplifier and showing you that my signal comes along with a common mode which I want to reject, right? And so one has to worry about what is the limit of this differential pair in terms of the common mode input that it can handle here. Let me show you a differential pair. All of you know is a part of a op-amp. So look at this case also. If you look at this case, a buffer, and suppose I apply a 3 volt sinusoid. So this is a 3 volt sinusoid, and you come back here. This also obviously is a 3 volt sinusoid. So note that the input common mode voltage is 3 volt. Input common mode voltage is 3 volt. If my differential pair cannot handle a common mode input of 3 volt, then the whole thing will not work properly here. So a circuit like this, you can see here, has a large input common mode range. While another circuit like this doesn't have an input common mode range. You know, when you operate it in a inverting amplifier, then this is 0 and this is 0. So it has a very limited input common mode range is not important. Whatever voltage you apply, this remains 0. right? So for such circuit, common mode range is not important, but for a circuit like this, input common mode range is highly important here. Okay, so we have to worry about what is the common mode range here. All right. This is what is illustrating, the simulation results illustrate what happens as I change the common mode voltage here. So note, I have a normal differential pair here. And what we have done is, to this differential pair, if you note, we have connected a 5 millivolt differential signal. Note that this 5 millivolt comes across this one here. So 5 millivolt is differential signal, and common mode voltage is here. This is common. VIC, as you can see here, goes here as well as goes here. So that's the common mode signal here. And 5 millivolt is a differential signal here. All right. So what I'm doing is, now I'm looking at the differential gain of this circuit as a function of VIC. I'm changing VIC. All right. So this axis that you see here is VIC, common mode voltage here. And I'm measuring the differential gain. How do I measure the differential gain? I'll measure the voltage here divided by VID will give me the differential gain. All right. So what I've done is I've plotted the differential gain that you see here, this red line, as a function of VIC here. So as expected, differential gain doesn't change with VIC in this particular case. We don't expect it. But what happens is, as you make VIC larger and larger, note that what happens is differential gain abruptly drops to very low value. Which means what? That there's a limit on how large a VIC I can apply. If I apply a VIC larger than this, my differential pair is no longer working properly because it doesn't give me gain. Right? So there's an upper limit on VIC that I can apply here. Similarly, as you go on the lower side here, you see something happening here. The gain starts building up and then again drops to very low value here. Right? So again, there's a lower limit here. There's a lower limit on how much VIC I can operate here. If you are in this range here, from this point to this point, then it's okay. But you can clearly see there is a positive upper limit here and there is a negative upper limit here. Similarly, here what I've done is I've plotted the common mode gain here. So common mode gain of this circuit is a differential pair and common mode gain as a function of VIC. So common mode gain again is very low. But what happens is, as I go on the lower side, you can see here, common mode gain is rising. Common mode gain is here is very small. You can hardly see it. All right, because it's 0.00 something. So here is very small. But then as you go to lower, common mode gain is rising, which means that my differential pair is not useful anymore. A larger common mode gain means it's no longer useful here. So the whole point behind all this data is that there's an upper limit here and there's a lower limit here. Within those limits, differential pair will work fine. And we have to understand what is this. And this upper limit is what we call as input common mode range positive, ICMR plus. And similarly, this lower range is what we're calling as ICMR minus, input common mode range negative. And these two are very, very important parameters of a differential pair. Okay. All right. So let's calculate ICMR plus. So the issue is, why is it that my circuit fails when I apply a very large VIC here? So the basic reason is, keep in mind that your differential pair will work properly as long as all the transistors are in saturation region. If any transistor comes out of saturation region, the differential pair will stop working properly. Okay, so let's see here. So when I apply 0, 0 here, I'm taking 10 by 1, 10 by 1, 10 by 1 here, and we have applied minus 2.41. Just as an example, the current here is 20 microamperes. Okay, so that's my case when I apply 0 input common mode voltage, and that's my normal bias point. All right, so here, and I can also calculate this is 2.21 and 2.21. This is nothing but 3.3 is my supply voltage minus the source gate voltage drop. All right, so that's the situation at 0 bias here. All right, now I increase the value of VIC. As I increase the value of VIC, what will happen in my circuit? What's going to change? Note the current is constant, 20 microamperes. So the current will split between the two equally because the circuit is symmetrical. If the current is the same, the current here is going to be 10. The current here is going to be 10. This voltage will remain constant, right? This voltage will remain 2.21. So what will change in my circuit? Everybody sees here that what will happen to this voltage is, because the current remains the same, and therefore if I increase this, what will happen to this? This will also increase, right? Because my current is remaining constant. Okay. So now note the present value of this voltage is minus 1.37. Now I'm going to change this to 1 volt. 1 volt. So what do you expect it to become? If you neglect body effect, then VGS should remain constant. So this should increase by plus 1 volt. And so this should become minus 0.37. But because of body effect, what happens is, as this voltage changes, note that the threshold voltage changes. So VGS does change a little bit here. Okay, but in general, what you note here is that this one, now if I do an accurate calculation, becomes minus 0.54. Without body effect, it should have become minus 0.37. It has become minus 0.54. All right. This voltage, 2.21, remains the same. Now, can you see what will happen as I further increase it? Now, what will happen is, if you look at M1, M1's drain to source voltage is, what is happening to it? Reducing. It will steadily reduce because this voltage is fixed. As you keep on increasing VIC here and VIC here, this voltage will keep on rising. And as it keeps on rising, the drain to source voltage of M1 will keep on falling. Eventually, a stage will come where M1 goes into linear region. And the moment M1 goes into linear region, note that what will happen is that the output resistance of M1 and M2 goes down, transconductance goes down, and the gain and all that will go down here. All right. So that's the phenomena that we are talking about, that at a sufficiently large VIC, M1 and M2 will go into linear region here. All right. So the focus, what determines ICMR plus is these transistors that are shown in red, M1 and M2. Okay. So now this is a slightly simplified analysis that I'm doing. So what we are saying is the value of this node is minus VGS. This is the bias point. This is the bias point here. Note bias point meaning if this is 0 and this is 0, the voltage here is minus VGS 1, which is same as VGS 2. When I apply VIC, it simply rises by VIC. So I'm ignoring body effect. Okay, VIC here. So this is this voltage here. The voltage at this particular point is VDD minus the source gate voltage drop here, VSG3 here. And so our interest is in VDS of this transistor. So we write down VDS1, which is equal to VD1 here, minus the source voltage here. And so we write it down VDD minus VSG3 plus VGS1 minus VIC. And we have to make sure that this VDS1 is always larger than saturation voltage, VSAT1. And so we write this down here. And this gives us that VIC has to be less than this particular limit. Okay, so it shows that there's an upper limit on how large a VIC I can apply. The next thing what we do is, so this is what we call as ICMR plus. This thing here, VDD minus VSG3 plus VGS1 minus VSAT1 is ICMR plus. That's the highest common mode voltage that you can apply and still ensure that all the transistors are in saturation region, which means the differential pair works properly. Okay. Next thing is we can plug in the expression for VSG3 and VGS1. So VDD is here, VSG3 is VTP, and normally you would write as 2 IDS by beta. 2 IDS of this is nothing but ISS. Okay, so ISS by beta. So that's your VSG3, and VGS1 is basically VT plus VSAT. Note that VGS of this particular transistor will be equal to VT plus VSAT, and VSAT cancel each other. So that's why you get VT. Okay, so this is what is the expression for ICMR plus. Note that what will happen is VTN and VTP. If you look at these two, they will tend to cancel each other. This is a small quantity here. And so you will find ICMR is pretty good, close to VDD. And in fact, due to body effect, what happens is VTN becomes much larger than VTP. And so ICMR plus you can get larger than VDD. So ICMR plus is a very good quantity here, which means you can apply common mode input, which is as large as VDD. Okay, so let me give you an example. This is another way of looking at it here, is the same diagram that I've plotted. The voltage at this point is minus VGS1. At the source, this is minus VGS1. The voltage at this particular node is VDD minus VSG3 here. VSG3 here. And we have to make sure that the transistor stays in saturation region. So this is VSAT1 here. And in it, the gap between these two is what is ICMR plus. So that's the same thing depicted in this particular form of a diagram. All right, let me give you an example. The same example here, 20 microamperes. If I plug in all the values, VDD, VTN, VTP, and all of that, we get ICMR plus as 4.1. Even though the supply voltage is 3.3, ICMR plus is 4.1. And the reason you can see here is VTN is large because of body effect. Large body effect makes VTN large. And so VTN minus VTP and all of that gives us 4.1. Okay. And so ICMR plus is 4.1. And when we simulate also, it gives us a very close value here, 4.177. All right. So there is an upper limit on how large a VIC you can apply. Fortunately, that limit is, larger than VDD here. So normally it will not bother you. If you make sure that your signals and everything are less than VDD, ICMR plus will not bother you in this differential pair here. Okay. All right. Will not bother you in this case here. But note, we have already seen that if you want to build amplifiers with higher gain, you replace a resistor by a current source here. And if you want even higher gain, you replace it by stack it like this here. Same thing you can think of here, as we have said, differential pair with resistive load, differential pair with current mirror load. If you're not happy with the gain here, what you do is just like you stack two PMOSes, you stack two PMOSes here. You can do that. All right. Now you will see ICMR plus will bother you, because now earlier there was a drop only from here to here. Now there are going to be two drops here. Okay, so now it will begin to bother you. You can easily show here. We leave it as part of homework problems that ADM is equal to GM1 R02. Note that GM1 will come from M1 and M2. That's the Norton's current will come out to be GM1 times VID. And the resistance here will be resistance looking down, which is R02, and resistance looking up, which is this combination here, R07, G7, R04 here. So overall gain will be basically limited by GM1, R02. And common mode gain, I'll leave it here. This is what will happen to ICMR plus here. ICMR plus, remember, is determined by M1 going into linear region. And so we have VDD here. We have one drop, VSG drop that you see here. Then as you come here, you see another VSG drop here. So you come at this particular point. This particular point is minus VGS1, and you have to ensure that M1 remains in saturation region. So you have VSAT1 here. And so the gap between these two is your ICMR plus. So you can clearly see that as you try to build up gain by stacking transistors here, what happens is ICMR plus goes down, right? So we can, by calculating all of these, we can find out what is ICMR plus here. So that's one. If we want to build up gain even further, you may want to make this a cascade stage here. Remember, this is a cascade combination here. And this is another cascade here. So you can build up a diagram like this. VSG3, VSG6, VSAT8, and VSAT-M. Can you see why VSAT8 here and VSAT-M1? Which transistor will go into linear region here? Is it M1 which will go into linear region or M8? M1, everybody sees. This point is fixed. And this source also is fixed by what? This V bias 1 minus VGS1. So source also is fixed. So M8, you have to bias it in saturation region. So this node becomes a constant voltage node here. And this node is what keeps on going up as you change VIC here. So M1 again comes out of saturation region here. So you can build a diagram like this here. VSG3, VSG6, two of them. This is a saturation voltage drop here, VSAT8. And you have to keep M1 also in saturation, so VSAT1. And this is VGS1 here. So you can see ICMR plus is shrinking. As you stack transistors, you can see ICMR plus is shrinking here. So this is a trade-off that is there here. And the issue is then, how do I build up gain without losing ICMR plus? All right. So there is a trade-off that you see here. If you want to build up a lot of gain, you have to stack transistors. And as you stack transistors, you're losing ICMR plus here. Okay. So it raises an issue of how do I use a cascade load? How do I use a cascade driver stage here without losing the ICMR plus here? And we'll see later on a solution to this particular problem is folded cascade that we had done earlier. Folded cascode, which was not very important earlier, you'll see will make sense here, a lot of sense here. Okay, so we'll come back to it later on. ICMR minus. All right. So let's see what happens when I take VIC on the negative side. I start reducing. So obviously, I'm sure you can see that as I go from 0 to -1, what will happen is this voltage will become more and more negative. And now what happens? M5, note that what will happen is VDS of M5 will start shrinking, right? Because this node is fixed and this node is falling. So M5 VDS starts decreasing, and eventually M5 will come out of saturation region, will go into linear, right? So again, the differential pair will fail to work properly here. So the same phenomena here, you apply -1, this becomes -2.18, and this remains here. So now the issue is of M5 going out of saturation region here. All right. So the focus now, remember, ICMR minus is determined by this transistor here, the bias transistor here. ICMR plus is determined by M1. ICMR minus is M5. All right. So same thing we have to do here. We calculate this voltage, which is minus VGS1 plus VIC here. This voltage is fixed, and we calculate VDS5, which is the difference of the two. And we have to make sure that this difference is larger than VSAT5. And so we plug in all the values here, and it tells us that VIC must be larger than this value. And we put in the value of VGS1. So ICMR minus is VSS plus VGS1 plus VSAT5. VSS is negative. And we rearrange after plugging in the values. We get ICMR minus is so much here. Now note, ICMR minus is low. Low, why is it low? This is minus 3.3. These are small quantities, but VTN is positive, right? So ICMR minus, unlike ICMR plus, where you could go beyond VDD, you could go up to 4 volt. ICMR minus will always be larger than VSS here. All right, so let's do some calculation and show you. A similar diagram can be built up here as well. The focus is here. So if you focus here, this is minus VGSQ here at this particular point here. This point is VSS here, and you have to ensure that transistor stays in saturation region. So this is VSAT5, and the gap here is ICMR minus. All right, let's put in some numbers here. Minus 2.2. So you can see here ICMR minus, you're not able to go up to negative supply rail. For ICMR plus, you're able to go to positive supply rail or even larger, while ICMR minus is only minus 2.2 here. So that's a big limitation, that I'm not able to go to my negative supply rail. Okay. Now, something interesting occurs here. All right. And further problems occur. If you recall, this gives you a particular CMRR. If you want to increase CMRR, we said you have to stack transistors. And if you stack transistors, what will happen is there'll be a drop here and there'll be a drop here. I'll skip some of these as a homework problem. You can see it later on. What will happen is you lose ICMR minus further. ICMR minus will become even smaller. To begin with is small, and if you stack transistors, it will become further smaller. Okay. All right. Now, what is interesting is the following. Note here, if we look at this circuit, what we found is ICMR plus is pretty good, and ICMR minus is bad. It has a low value. If I go into PMOS, what will I find? Note here, we will find ICMR plus is good, bad. ICMR plus is bad, ICMR minus is good here. All right. So, example, ICMR plus for a PMOS differential pair here is 1.89, and ICMR minus is minus 3.3. Okay. So, here is the situation now. All right. ICMR plus is good, goes beyond VDD. ICMR minus is poor. PMOS differential pair, ICMR plus is poor, ICMR minus is good. So what do? Combine them, right? So you're saying combine both of them. And how do you combine two differential pairs? Now, it's not straightforward, but that's what people do here. They will take this differential pair and they'll take this differential pair. Input will be applied to both here, and we'll see how to combine both of them, so that we'll take ICMR plus of this differential pair, and we'll take ICMR minus of this differential pair and get a ICMR plus, which is rail to rail. All right, so that would be the strategy that we'll use later on to combine both of them. But combination is not trivial. Combination is, how do you connect them in parallel? All right, so it's not trivial, but we'll see. That's what you do, and then you obtain a differential pair, which we call as a white swing differential pair. But keep in mind, the swing that we are talking about is not output swing, is the common mode swing that we are talking about. So we can call it as a white swing differential pair. All right, so that's input common mode range. Let's come back to output swing. Now, normally output swing is not of interest to us because differential pair is an input stage, and therefore the input stage will be followed by further stages, right? So normally we will not bother about a swing here. But suppose you are interested in using a differential pair as a standalone amplifier. If you try to use a standalone amplifier, you'll see the swing is an issue here. Okay, so let's look at the swing for a moment. All right, so here I've put a ground here and applied a differential voltage here. And differential voltage that you see, what it will do is, if I do a KVL, this is nothing but VGS1 minus VGS2, right? VID. If you go from here, come here, and then go here, you get VID is VGS1 minus VGS2. Okay. All right. If you increase VID, what happens? If I increase VID, VGS1 will go up and VGS2 will go down, right? That's what happens here. Now, as you increase VGS1, what happens? Current here should increase and current here should decrease, right? That's what you expect, okay? And IDS1 will become larger than IDS2, okay? Which implies that this current will become larger than this. Does it bother you? This current becomes larger than this? How can this become larger than this? It's a current mirror, right? So how will it become larger than this? So what happens is, see, as you increase VID is made positive. VGS1 has to be larger than VGS2. So we require IDS1 to be larger than IDS2. They are in series. So we require this current to be larger than this. But you see that both transistors are identical. Their gate to source voltage is also the same. So how can this current be larger than this? What will happen to M4? M4 goes into linear region. M4 goes into linear region here. When M4 goes into linear region, its current becomes smaller and smaller. Linear region means V0 starts approaching VDD, right? Eventually what happens is, if you make VID very large, the entire current will shift to M1. Entire current will shift to M1. So you have a lot of current here. You have no current here, M2. Now, if you have a lot of current in M3 also, which means that M3 is biased. M4 is also biased above threshold, but the current here is 0. What will happen to V0? V0 is VDD, right? So what happens is, so you're seeing what will happen is, as you increase VID, more and more current ISS will shift here and V0 will start approaching VDD. Eventually, everything flows into M1. Current here is 0 and V0 is equal to VDD, right? So that's what is happening here. So this is what you see here. Increasingly, the current IDM1, red one, is increasing. IDM2 is decreasing here. And this is what the red line shows here, what happens to output voltage. Note the output voltage here. Output voltage starts, goes here, and eventually comes to 3.3. So what does it tell us about the positive swing? It's very good. It goes right up to VDD here. So positive swing is not a problem. Now the problem will come when I make VID negative. Now I want V0 to become negative. All right. So now see what will happen is. So you get good positive swing, no issues. All right. Again, same thing. As VID is decreased, we are now making VID negative. VGS1 decreases, VGS2 increases. What should happen? IDS1 should become less than IDS2. ISD3 is less than ISD4. Can this happen? Can this happen? Both transistors are in saturation region. I mean, this is in saturation region, right? And gate to source voltage is the same. Now, remember, there is a zero phase difference between VID and V0. So as you make it negative, this point comes down. So this is also in saturation region. So how can this be ISD3 be less than ISD4? So what happens now? What happens in this differential pair now? Of course, the currents in these two are not going to be identical, because what will happen is, while this voltage is, as you shift current onto this side, the current here reduces and this voltage falls. But then what happens is, even though they are in saturation region, the voltage here is different from voltage here in general. So current here can be a little bit larger than this, but not too much. Why? Because both of them are in saturation region. When both are in saturation region, the current here can be larger than current here, but the difference will only come about because of channel length modulation. And that is not too large a quantity here. Okay. So see what happens here. As I make my VID negative, all right, VID negative. So I start from 0, minus 40 and all of that. So see what happens here to this, to the two currents here, ID M1. We want ID M1 to become small. It does become small, but not by much. ID M2 should become large, but also increases, but not by too much, right? Because the differences can only come about because of channel length modulation, and that's not a very strong effect. So to a first order approximation, what you can say is the following, that the current switching doesn't occur. The current does not, ISS does not switch to this transistor here. Very little of it goes here, and some difference occurs here. Some small differences occur here. So now what is happening in this? You have made VGS1 is less than VGS2, but how come the currents are the same then? Focus on these two, M1 and M2. VGS of this transistor is less than VGS of this transistor because I've made VID negative. So how come the current in M1 and M2 are comparable then? M1 goes to linear. How does it go to linear? Why should M1 go into linear? So first order approximation, keep the following thing in mind. Let's say this is 20 microamperes. Let's say this is 10 and 10. Let's ignore this one here. So 10 and 10, it remains 10 here and 10 here. Now you're making this voltage more and more negative. As you make it more and more negative, what happens to this voltage? This becomes more and more negative. So what happens to VGS1? Becomes smaller. And what happens to VGS2? Becomes larger. Then how do you explain this? First order, what do you think will happen? If current switching doesn't occur, if current remains the same 10 microamperes, then VGS1 of this should remain same, constant. Agreed? So if let's say if initially this is minus 1.5, if I make it minus 1, this will become minus 2.5, VGS remains the same. Fine. So current is the same, no problem. But then VGS here has increased so much. So how do you explain? Current here is also 10 microamperes. So how do you explain that? How do you explain M2? What is happening in M2? Huh? So see the problem. I'm making VID negative. Therefore, VGS2 has to become larger. And if VGS2 is becoming larger, but current is remaining constant, is that possible? VGS of a transistor is increasing, current is remaining the same. How is that possible? M2 is in linear region, and now see what happens is, so M2 is in linear region, and once M2 is in linear region, this is the equation that is there. All right. Now what happens is, as M2 is in linear, you are increasing VGS2, right? VGS2 is increasing, but what is happening to VDS? VDS is decreasing. So what happens is, this voltage is becoming lower. This voltage is becoming lower, and the effective drain to source voltage becomes lower here, and that counteracts the increase in VGS. So VGS becomes small, but VDS also becomes, VGS becomes larger, VDS becomes small, maintaining almost the same current here, right? So what is happening is M2 goes into linear region. And as M2 goes into linear region, what will happen to the drop VDS here? VDS becomes small. How small can it become? At the most 0, which means that V0 can at the most approach this voltage here. And how much will this voltage be? What do you think will this voltage be? You can see here, this voltage is around minus 1.2 or minus 1.3, depending on the current here, right? Depending on the current here. So what happens is, this voltage on the negative side can at the most go to this voltage here, source voltage here. And note, the source voltage, if I compare to ground, will be a 1 VGS drop below. And therefore, you can see here, this red line is showing you where V7 goes. V7 goes at the most to minus 1.2 or minus 1.3. So the message behind all of this is, V0 on the positive side can go up to 3.3. On the negative side, V0 can only go to this source voltage here. And the source voltage is below 0 by about minus 1.2, minus 1.3 or so. So negative swing is pretty bad here. Negative swing, we want it to go to minus 3.3. It can only go to minus 1.2 or so. So that's the problem with the differential pair as a standalone amplifier. Positive swing is pretty good. Negative swing is only till here. Okay? Yes.
This is going in saturation region.
Which one? M2. M2 is not going into saturation.
Linear region.
Then
whatever the amplifying.
It will not. No, once it goes, it no longer amplifies. So this is what is happening. You can see here V7 starts to change. The moment it goes here rapidly, after that V7 is not changing with input voltage here. V7 is not changing here. This is the output, which means there's no gain. So there's a gain here till this point here. V7 is changing here. So there's a gain in this particular part, but once it saturates, then there's no gain. Okay. So gain is in this. So all that you could do is you could come up to this particular part here. After that, you will start getting clipping. It will start getting clipped at minus 1.2. So minus 1.2 is what is the swing that you can get on the negative side. Positive side is fine, goes up to 3.3. Okay. So effective swing then of my differential pair is 1.2 volt here. 1.2 here and 1.2 on the positive side. Because it will get limited by this side here. Okay, so that's the limitation on output swing. So poor negative swing here. All right. And of course, then if I make a PMOS differential pair, it will have a good negative swing and a poor positive swing here. All right. So you may want to combine both of them also. All right. Now, this is something that I wanted to point out, which most of the books will not talk about. If you look at this differential pair, we said there's a current switching. Note that when you go VID positive here, the current in M1 becomes larger and current in M2 becomes smaller. When I go VID negative, the current in M1 becomes smaller and M2 becomes larger here. But when you go to a differential pair with a current mirror load, it doesn't happen. There's a slight mistake here that the positive axis is on the left hand side, negative axis is on the right hand side. Okay, so keep that in mind. So what happens is when I make VID positive, there is a current switching, right? When you make VID positive, current in M1 starts increasing, current in M2 starts decreasing, just like here. But when you make VID negative, there's no current switching. Currents in the two are almost the same. All right, so this is a big difference between these two amplifiers here. When you don't have a current mirror load, you have a nice balanced circuit here. VID positive, VID negative is the same. When you go here, you can see the differences here. No current switching when VID is negative. Current is not able to switch. Okay. All right, so it's the same thing. As I said, output swing. If I look at output swing here, it can go up to 3, only goes up to minus 1.5 or so. This is a PMOS differential pair, has a poor positive swing, has a good negative swing here. All right. Okay, so we're done with the output swing here. So it's not so suitable for as a standalone amplifier for that reason. Frequency responses, we'll do a very simplified analysis. We'll assume that the differential pair is being driven by a low resistance source here, and 3 dB frequency is determined entirely by the output node here. So basically the net capacitance at this node, sum of all the capacitors due to PMOS and NMOS here. So drain to body, gate to drain of both the transistors, sum it up. Resistance at this node we know is R0. So we are considering only one time constant. This is a low impedance node because 1 by GM, and we are assuming that this one and this one is also a low impedance node. That is, we are connected a source here. Source resistance is very small. So under that assumption, there's only one high impedance node, and the 3 dB frequency is simply 1 by 2 pi R naught, 1 by sum of the capacitance here. Gain we have already seen is GM R02 parallel R04, and the product of the gain and 3 dB is what we call as unity gain frequency, and that simplifies to GM by 2 pi, the total capacitance. All right. So one of the parameters that people quote for a differential pair in an op amp is unity gain frequency, and so unity gain frequency is the product of these two, GM by 2 pi C total. All right. Okay, so this is just example here. All the capacitors that you see here are not is here. 3 dB frequency comes out to be 8.5. UGF is 1.5 gigahertz here. Okay. All right. This brings us to another interesting point of a differential pair here. If I now look at my differential pair, I can write my differential pair at this point here, output node, in terms of a Norton's current, GM1 VID, a Norton's resistance R0, and now I've added also a net resistance, net capacitance at this particular node, which is C total. Okay, so to bring in the frequency analysis part, I've added this one here. And our 3 dB frequency was nothing but 1 by 2 pi R naught times C total, right? So this is a model that we are building there at this particular node. So we've added a C total. Now I can write it in the form of a Thevenin's equivalent also. I can multiply these together and write it as GM1 times R0, which is ADM, and then R0 goes in series, and then I get C total, right? So that's the model of a differential pair from looking at from this side here. Okay. At low frequencies, we neglect C total. At other frequencies, we have to include C total. All right. Okay. Now, this is where it's interesting. Is this R0 C total that you see here is an RC circuit, right? And in an RC circuit, you know, if I look at a transient response, so the idea is the following. Suppose I apply a differential input voltage, a step. Okay, a small step that I apply here. What will happen is this will also be a step, right? So now I have a step, and what will happen to V0? It will start charging. And similarly, if the step is from high to low, it will start discharging. So what I expect is that I should have an exponential charging and an exponential discharging. This is a simple RC circuit, right? Which is fine. It works okay. You can see exponential charging and exponential discharging. The trouble comes is when I make this value a little large. ADM VID. So as I raise the value of VID, a stage comes when it goes like this here. It no longer charges exponentially and discharges exponentially. It charges linearly and discharges linearly here. So the idea is that if you make the input a little larger, it changes its character. It's no longer charging exponentially and discharging exponentially. Is going like this here. Charging linearly and discharging linearly. So the issue is what happened. Obviously, this model has failed because this is the exponential characteristics, and now this is linear here. So this model has failed, and the issue is why has it failed, and what is this phenomena here? Now, many of you may already know that when output voltage changes linearly like this here, we call this as a slew rate. Slew rate in an op amp, must have heard earlier. Op amp, charges linearly like this here, discharges linearly here. So this phenomena is called a slew rate here. And where does it come from? It comes as follows. So this is important to understand because this is there now forms the basis of slew rate of an op amp. Okay, so this differential pair here. So now what you have to understand is if I apply a step here, why is it that if this step is a little larger, why is it that it charges linearly here and charges and discharges linearly here? So you have to keep in mind, this is a differential pair. I have some net capacitance here. Now this capacitance that I've drawn is capacitance due to M4, M2 and all of that. Plus there may be a load capacitance also. Okay. So a total capacitance. Now what happens is the following here. As I apply a step, now note if the step is large, what will happen? Let's say it's a positive step. If you apply a large positive step, now remember, if I apply VID positive, what happens? Current switching occurs. Keep that in mind. VID negative, current switching doesn't occur, right? So VID positive, if the step is a little large, then what will happen is the entire 20 microamperes current will switch to M1. Okay, so it will flow to M1, and current in M2 will go to 0. Now this M1, the same current will flow in M3. So same current is in M3. What will flow in M4? What will flow in M4? So now note the following. Let's assume the following. Let's assume that initially this voltage is some low value, let's say minus 1.5. Okay, some minus 1.5. Remember, negative swing was how much? Minus 1.5, right? Minus 1.2 or minus 1.5. So let's assume that this is initially minus 1.5. Suddenly you've applied a step. Entire current 20 microamperes shifts here, goes here. Now this is still at minus 1.5, which means M4 is in, if this is minus 1.5, this is 3, M4 is also in saturation region. If it is in saturation region, the current in M4 has to be same as M3, which means 20 microamperes flows here. But then this 20 microamperes doesn't flow into M2. M2 current is 0. Where does it flow? It charges the capacitor. Alright, so it goes here. So it starts charging let me explain here. So when you apply, let's say 200 millivolt here, 20 microamperes starts flowing here, same current goes here, current here is 0, it starts charging this. And now note that it's a constant current which charges the capacitor. And therefore you see a linear variation here. And so dV0 by dt is equal to ISS, which is this 20 microamperes, divided by CL. CL is the net. Instead of actually calling it load capacitance, you should call it as a C total capacitance at that point. So you can see here, that's why output voltage charges linearly here. RC circuit, on the other hand, assumes, note that, let's go back and look at RC circuit. RC circuit, what is the charging current? Initial charging current when you apply a step? No, initial charging current in an RC circuit. Initial voltage on the capacitor is 0. You apply a step, the charging current is whatever is the voltage divided by R0. So this circuit says that as you keep on increasing the step, the charging current keeps on increasing, right? And it requires that for an exponential characteristics. But note, in my differential pair, I have a limitation on current. If I apply a small step here, what would happen is the charging current will not be 20 microamperes. Then this circuit is valid here. See, initially, if you apply a small step, then the current requirement is ADM VID by R0, right? Or whatever is the charging current. Then that much current is able to flow. But if you apply a large step, then there's a limit on 20 microamperes. So when you apply a small input, then the circuit is like an like a RC circuit, and it works fine. There's no limitation on current. But if you apply a large step, then that large step requires a large charging current, and that large charging current is not available. I have a limit on 20 microamperes here. I reached that particular limit, and then it charges linearly. Okay, so it only happens when you apply a large step. If you apply a small step here, then it's exponential, no problem. But large step causes a linear rise and linear fall. Okay, and this phenomena is what we call as a slew rate. This dV0 by dt, the rate at which the output voltage changes, is what we call as a slew rate. So what it says is, this is the maximum rate at which V0 can change. V0 cannot change at a higher rate than this, because the charging current cannot be larger than ISS. Okay, so that brings a limitation to a differential pair, that there's a maximum rate of change of output, which is dV0 by dt is ISS by CL. Alright, something very interesting occurs when you go to negative. Now, negative, what did we say in negative? We said that current switching will not occur. If current switching doesn't occur, then how will the capacitance discharge? Let's say this is 20, this is 10, this is 10, this is 10. Then how will the capacitance ever discharge? So now keep that in mind that this voltage has gone to, initially is 3.3. 3.3, right? Is positive swing. Positive is charged to 3.3 here. Suddenly now you bring it to a large negative voltage. If you bring it to a large negative voltage, we are saying that current switching cannot occur. Then if current switching doesn't occur, if this is 10 and 10, if this is 10, then this has to be 10. Right? Because when you apply a negative swing, this voltage will become even more negative. Right? So this will also stay in saturation region. So how will this capacitor discharge? See here. You have to go back and think of why did we say that current switching cannot occur? We said M2 was in linear region. But remember, this is 3.3 initially. Until the capacitor discharges, this cannot go in linear region. Cannot go into linear region. So when it starts with 3.3 here, this is in saturation region. So then what happens? Actually, current switching occurs here. What happens is when you apply a minus 200 millivolt, this 20 microamperes, what will happen is it actually becomes zero temporarily. It becomes zero because note that both transistors are in saturation region, so it does go to zero. This becomes zero because if this is zero here, M3 is not biased then anymore. If M3 is not biased, M4 is also below threshold. So current here is zero. What happens is this current is 20. Temporarily the current switches entirely here and it begins to discharge. As it begins to discharge, eventually what will happen is M2 will go into linear region and then the current will start to balance and it will become 10 and 10. So initially, so what happens is current does switch under transient condition, current does switch here. And 20 microamperes current discharges CL here. And then the discharge is also dV0 by dt is ISS by CL. So it discharges at the same rate. Okay. So charges at the same rate and discharges also at the same rate. So current switching does occur, but temporarily as it goes into linear region, then this instead of 20 microamperes, it becomes less and this starts climbing because the sum of the two currents have to be the same and eventually they both become comparable. All right. So that's the phenomena that is occurring in when you apply voltage steps which are large, such that the current switching begins to occur here significantly. Okay. All right. One by one, we are going through all the parameters. Noise. Well, you have 1, 2, 3, 4, 5. All these noise currents are there. Fortunately, there's a lot of symmetry in the circuit. So I need to do calculation for M1. Same thing holds for M2. Similarly, I need to do calculation for M3. Same thing holds for M4. And I need to do a calculation for M5. So three currents are three independent calculations I need to do. And for each one of them, I need to find out what is V0, noise voltage due to this one, noise voltage due to this one, and noise voltage due to this one. All right. So each one of them you have to do. All right. Does this make sense? Look at this diagram. This is the noise current I'm interested in. What will be IN then? IN is equal to Norton's current I'm calculating. Because Norton's resistance at this node I already know, which is R02 parallel R04. So what will be IN? Well, look at this. So it's a floating current source. So IN1 goes here at this point. It has three choices, I1, I2, I5. Where will it go? It will go here and here, right? And will I1 be equal to I2? So our approximation is nothing goes in I5. It's a high resistance. What do I see here? 1 by GM. What do I see here? So equal. So let it divide equally. So I1, so this is equal to IN1 by 2, right? I1 is equal to IN1 by 2. Alright, so I come here. So how much is this current then? IN1 by 2. How much is this current? It's a mirror. IN1 by 2. How much is this? IN is equal to? IN is equal to basically IN1. So notice current is the same current here. Device comes here and all of that, eventually IN equal to IN1. So,
Why there is a 1 by GM1 for I1?
hmm.
Because that the trend of M1 is not sorted.
No, but this is 1 by GM3, right? So when you look from here, what do you get? Resistance is 1 by GM1 multiplied by 1 plus this resistance divided by R0. So 1 by GM divided by R0, very small, negligible. Okay. So this one divides equally here, goes here, comes here, and then eventually it all adds up to IN1. And we know that noise voltage at the output then will be IN1 times R0, net output resistance here. Okay. All right. Look at this one. Look at this current here. Starts here, goes here, goes here, some goes here. How much is IN then? Norton's current equal to IN3, right? So note that as it comes here, let something go up, let something come down. So as it comes down here, it has a choice. It's not going to go here. It will go here. As it goes here, it will eventually come out. So the same I1 component is traveling here and is coming here. And whatever is this component is getting mirrored here. So the sum is again IN equal to IN3. Which one?
IN3 minus I1.
Uh-huh.
We are on 0.
What?
That component.
This component, yes.
We are on 0.
No, that's okay. Whatever it is, whatever is this component is going to be mirrored here, and the sum will turn out to be IN3, right? Okay. So the output is then equal to simply IN3 times R0. Okay. So we have determined the noise voltage at the output due to this one also. Same thing will happen to IN4 also. Okay. So whatever happens to noise volt current here, same thing here. Whatever happens here, same thing here. Now, should I do the calculation for this one? Or is not required? Why is it not required? You already know how to carry out these calculations? Or I should not even do it. I should just say its contribution will be negligible. I'm making a more stronger statement. Not that you know how to do it, but I'm saying maybe we should not even do it. Just forget about it. I should not even do the calculation for IN5. Why? No, don't go through the calculation. Why am I saying that IN5 may not contribute much to noise? There's a reason why I'm saying it. Without doing any of the calculation, I'm saying IN5 will not contribute much to my noise. Huh? It's a common mode. Note here, it's like a differential. It's there on this side, not there on the other side. Right? Similarly, you go here, this was there on this side, it's not there on this side. This is a differential signal. And differential signals have an impact. This one is a common mode signal here. And common modes, and remember, the property of a differential amplifier is anything which is differential is amplified or is sensitive. Anything which is common is rejected. So it will get rejected here. Let's see. So now you can see, I'm sure you can see what will happen is this current is there. What will happen? It will go here or here, right? Now, if it goes, this point is 0, this point is also close to 0. So it will almost equally divide between I1 and I2. So it goes here I1, and therefore it will get mirrored I1 here. This is also I2. You can see IN will be equal to I1 minus I2, and both are almost same, and therefore it's coming out to be almost zero. And it won't be perfectly zero, but you're seeing it's getting rejected. My Norton current is not sensitive to IN5. It's getting rejected by the circuit, right? And therefore this noise current will not bother you, will not contribute much. Okay. So next is we now know all of them here. So you now is more of algebra here. You can take a thermal noise, you can take flicker noise. So I'm going to skip all of that. Tell you what the final value is. That's the final noise voltage. Refer to the input. Now this expression is important because differential pair is an input stage here. The overall noise performance of an amplifier is all determined by differential stage. So if you're interested in low noise performance, you have to minimize this one. And how do you minimize this one? You can see you have to make transconductance large. Large transconductance means transconductance is square root 2 ID beta, right? So either you make beta large size transistor, which you are saying will increase GM1, and large size transistor will also make the second term small, right? So you make large size transistors and it minimizes both of these terms here. It makes GM1 large and it makes the second term also small, right? And therefore my noise becomes small here. So if you want low noise performance, make your M1 and M2 large size, 200 by 1, 500 by 1, something of that sort here, right? So large size transistors here. And the other thing is, of course, you may want to make current, bias it at larger current. That you don't want to do because the gain, what does gain depend on? GM times R0. GM goes as square root I and R0 goes as 1 by I. So gain is inversely proportional to current. So you don't want to increase the current. If you increase the current, the gain goes down, right? So a better approach is to increase the size here. Increase the size and note that this term, the flicker noise goes down also significantly here. So large size input transistors are beneficial for low noise here. Okay. All right. So some examples are here. This is 10 by 1, 10 by 1. So you get a noise which is 16.54 nanovolt per square root hertz. Okay, that's the last. we stop it here. Power supply rejection ratio. Now look at this. Power supply rejection ratios were pretty bad in the other amplifiers, right? Do you think they're bad here? Or will they be better than common source amplifiers? Again, this VDD that I've applied here is what? It's a common mode signal, right? Common mode signal will get rejected again, right? So now what will happen is power supply rejection ratio will improve. Okay. So now remember one thing. How do I do this calculation? I want to know what is V0 by VDD. How do I do it? It's a common mode signal. Should I attempt to calculate this V0 or should I attempt to calculate this one? Which one should I do? Should I attempt to calculate here or should I attempt to calculate here? Or both of them will be the same, agreed? Because of the symmetry, this voltage is going to be the same as this. We have said that when 0, 0 and all of that, the voltage here and the voltage here are the same. Okay, under common mode signal here. Calculation of V0 is more involved because it has all of this here. Calculation of this one is rather straightforward here. So we do the following. We apply VDD here. M3 is here. M1 is here. And because it's common mode, I can split it into 2R05 here. So we get this here. And how much will be V0? What is this, this one here? 1 by GM. And what is the resistance looking down? R01 multiplied by GM1 times 2R05. So it's a very large resistor and this is a very small resistor. So V0 will be equal to V0 will be equal to VDD. Yeah. So same V0 is VDD here. Okay. So my power supply rejection ratio then is ADM by 1. And if I have ADM of 100 or 200, power supply rejection ratio is of the same kind. Okay. So it is certainly much better than a amplifier that we had earlier. Remember, a common source amplifier had a transistor like this and another transistor like this, and there the PSRR plus was 1. PSRR was 1, and similarly PSRR minus was also 1, close to 1 here. Now you're getting PSRR plus is ADM. So it's a pretty good value of PSRR plus. Now same thing will happen here, VSS here. This calculation is slightly more involved. See whether you can follow these steps. This whole thing is replaced by GM5 VSS times R05. So the idea is build Norton's equivalent at this point here first. At this point, the resistance looking is R05. The net Norton's current here is GM5 VSS here. Okay. Now again, do the calculation on this side. Don't do the calculation here. Here is much tougher. Okay. And so we do the calculation on this side. Now note, does it make sense here, this step? Because the circuit is symmetrical, note this voltage is same as this. So we have split the current source along with R05. Current source becomes half, R05 becomes double. Alright, note that this splitting is being done equally between the left half and the right half. So we have here. Now what will happen? This current has 2R05 or will go up. And so the Norton's current at this point will be simply 0.5 GM VSS, Norton's current, and the Norton's resistance is 1 by GM. And these ones will almost cancel, so V0 by VSS is also close to unity. And therefore PSRR minus is also ADM. So you have a very good value of PSRR minus as well. Okay. Okay. So how tired are you? All right. So we are almost done with differential pair. This is something extra. Okay. All right. So the extra part is the following. It's not a part of the exams and all of that, but this is something which is also very important. Important in the sense that in all of these differential pairs, we are saying M1 is identical to M2, M3 is identical to M4. Real life M1 will not be identical to M2, M3 will not be identical to M4. And what is the consequence of that? So matching becomes very, very important. And this is a paper that I'll recommend to all of you. It's given here, IEEE Journal of Solid State Circuits, an early paper, 1989 paper here. And this talks about matching properties of MOS transistors. And for differential pairs, op amps, and many, in fact, most of the analog circuits, matching becomes very important. In current mirror, I want M1 to be matched to M2. In differential pair, I want them matched. And many other circuits, they rely on matching. And if there's a mismatch between the transistors, then that assumption is getting violated, and it has consequences here. Okay. Now, let's try and understand the mismatch. What do we mean by that? So look at this particular diagram here. Now, the mismatch that I'm talking about is the following. I don't know whether you recognize this green one is N plus and red one is poly. So there are two polys, meaning two transistors. So now suppose we do an experiment like this, that we make two transistors here. This whole circle is a wafer. It's a big wafer, 300 mm wafer. So I make M1, M2 here. I make M1, M2 here. I make here all over the place. Suppose I fill it up with two transistors here, right? Now I'm making them very close. I expect threshold voltages to be same, right? Exactly same process, everything same. Now suppose I measure of this transistor VT1 and this transistor VT2, and I take the difference, and we call it as delta VT. Delta VT. This is what I would find typically. Now understand what I'm measuring. I'm measuring the difference in the threshold voltage of these two transistors, right? Difference in the threshold voltage of these two transistors. Average value is 0. But then somewhere I will have larger value, somewhere I will have lesser value, and it's a random variable. And if you take large enough number, it would be a nice bell-shaped curve. All right. So what does it tell us? That if I randomly, if I pick a pair of transistors, I will find that the threshold voltage is different. Right? Threshold voltages differ. And it's a random curve. So how do I describe the mismatch between two transistors then? If you are asked for a parameter to describe the mismatch between two transistors M1 and M2, how would you describe? What parameter will you use to describe the mismatch? Say mismatch in VT. What would you use? Sigma? Standard deviation? It's like a bell curve, right? Gaussian curve. So you would use sigma, variance or standard deviation as a measure of how much is the mismatch between the two transistors here. So we use something called sigma. And sigma square, as you know, is variance. So sigma square now has something very interesting. Note that the sigma square, so the variance of the threshold voltage mismatch depends on, it's made up of two factors. One factor is AV is a constant and S is also a constant. Okay. So one factor is the size. The smaller the size that you make of the transistor, the larger the variance, which means the more the mismatch. So it's a very, very important point. If you're looking for very accurate matching between two transistors, make the size large. Then the matching between the two transistors is good. The other one is, this D is the distance between the two transistors. The larger the distance between the two transistors, the more the mismatch. So if your requirement is that your two transistors should be matched very, very well, what you should do is make their area large size transistors, and make the distance between the two transistors 0. 0. Make the distance between the two transistors 0. Right? Right or wrong? Huh? Wrong? You can't make distance 0? Why not? Why can't you make the distance between two transistors 0? Then short? Okay. Let me skip something. You're all biased by your this thing. Here are two transistors, right? Two transistors. Take some time to absorb this here. I'm showing a differential pair, M1, M2. Two transistors are there. Correct? How would you describe the distance between the two transistors? It's a large entity, so how will you describe the distance between the two? How would you say? A simple measure of distance? Maybe, what is the distance between the two? How would you define? How would you define the distance between? Well, you will say, where is the center of this one? Where is the center of this one? Right? Centroid of this one and centroid of this one, and you'll measure the distance between the two. That's a reasonable estimate. Centroid of one transistor, centroid of another, and you take the difference and you say that's the distance between the two. Okay? Fine. So you still think I cannot reduce the distance to 0? Let me see if I have somewhere. I'll skip and show you. All right, all these calculations will come. Look at this one first. Absorb this. This is D1, S, and D2, right? Differential pair. D1, S, and D2, right? Source is being shared by them. D1 is here and D2 is here. There is a distance between the two transistors, right? And therefore you'll have mismatch. Now look at this one. What has one done? What I've done is I've split my transistor M1 into two parts. Then I've split my transistor into two parts. There's a D1 and there's a common source, and this is D2. And there's another D1 here, And so what I'm going to do is the following. D1 I'm going to connect here, okay? And D2 I'm going to connect here, right? Now, so M1 has two parts. M1 is here and M1 is here. M2 is here and M2 is here. What is the distance between two transistors? 0. 0. So this is called common centroid design. I have 0 distance between the two transistors. They're symmetrical. M1 here and M2 here. 0 distance. Now, what do I mean by splitting a transistor? Well, splitting is, remember, I can take two transistors and connect them in parallel. And it's effectively a transistor will double the width. It's the same thing here. D1 here, D1 here, D2 here, and D2 here. Remember, input stage we are talking about. So we'll have a transistor maybe whose size is 50 by 1 or 100 by 1. Well, we'll split it into two. One is 25 by 1, 25 by 1. Combine them in parallel, and you get 50 by 1 here, 50 by 1 here, and you get matched. So input stage and all of these differential pairs and current mirrors, you do layout like this here. You split transistors, M1 here, M2 here, and you can split like this also. If you're very large, you can split like this, M1, 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 M1 here, M1, M2, M2, M2 here. And this is what we call as a common centroid design here. So for differential pairs, for current mirrors, wherever you require matching, the idea is use large size transistors, right? And you make distance between the transistors 0 through a common centroid design. Okay. All right. So some more implications of the mismatch we'll see. It contributes to what we call as input offset voltage of a differential pair. Okay. So we'll see that in the next lecture. So let's stop here.